All right, today we're diving into something really cool. We're going to see what happens when you take one of our most powerful technologies, yep, artificial intelligence, and use it to fix a huge problem for another, quantum computing. This is a deep dive into a project where an AI literally learns how to make quantum computers better.
We all hear about the incredible promise of quantum computers, right? But here's the thing. Unlocking your true power might not just be about building better hardware. It might be about finding a smarter way to program them. And that leads to this project's big question. What if an AI could actually learn to design more efficient quantum programs just by looking at a bunch of examples?
And that brings us right to the heart of the matter, what I'm calling the quantum efficiency puzzle. See, quantum computers are unbelievably powerful, but they're also incredibly sensitive. The programs they run, these things called quantum circuits, are super fragile. Every single unnecessary step, every extra operation, introduces noise and errors that can just wreck a whole calculation. So making these circuits as short and clean as possible, well, it's not just a nice to have, it's an absolute necessity.
Okay, so to crack this puzzle, let's start with the basics, the building blocks. A quantum circuit is really just a list of instructions, or gates, that you apply to quantum bits, or qubits. In the simple text format this project uses, a circuit could look something like this. That just means you apply a Hadamard gate, the H, to the first qubit, which is qubit 0. Then, you apply a CNOT gate, which links that first qubit to the second one. The real challenge? Finding the absolute shortest sequence of these gates that still gets the job done.
So how in the world do you teach an AI to make these circuits better? Well, like any good student, it needs homework. It needs something to practice on. A lot of something. So the very first step in this whole project was to create a massive library of these practice circuits.
And this is basically the assembly line for creating all that practice data. First, the code uses a library called Cirq to just generate a whole bunch of random quantum circuits. Then, and this is key, it simulates them, but it includes all the noise and interference you'd find on actual hardware. After that, it applies some standard, by-the-book optimizations, and finally, it saves everything, the original circuit, the noisy version, the optimized version, into a dataset.
And after that whole pipeline is finished, you're left with one single tangible file, Cirq dataset.jsonl. This thing is packed with thousands and thousands of unique quantum circuits. You can think of each one as a tiny little puzzle just waiting for a smarter, better solution. And that brings us to the really exciting part.
Now, we get to the main event. We're going to teach an AI to take these circuits and optimize them. But instead of using those standard pre-programmed rules we just talked about, this project takes a totally different and, frankly, much cooler approach.
So you can really think of it as two different paths. On one hand, you have the classic method. It's like having a fixed rule book from a library like Cirq. It sees a pattern, it applies a rule. Simple. But the AI method, using Google's Gemini model, it's a whole different game. It doesn't have a rule book. Instead, it just learns. It learns to spot the optimization patterns by looking at before and after examples, figuring out the rules for itself.
So how do you actually teach it? It's this amazing technique called in-context learning. You basically just show the AI a few examples in the prompt. You show it, hey, look, this unoptimized circuit here, it simplifies down to this optimized one. Then you give it a brand new unoptimized circuit, and you just ask, optimized, and leave it blank. It's a lot like teaching a student by showing them a few solved math problems instead of just handing them the answer key and expecting them to get it.
Okay, so that's the theory. But does it actually work? Let's put this AI optimizer into action and see what it spits out.
And this isn't some abstract idea. This is the literal command you type to run it. You call the script, and you just feed it an input circuit as a simple string of text. In this case, we're giving it 2 X gates on the first qubit, followed by a Y gate on the second one. So let's see what the AI thinks about that.
And boom! Here's the payoff. Gemini's output is just Y1. It correctly figured out that applying an X gate twice in a row is totally pointless. They just cancel each other out, and it got rid of them. Now here's the crucial part. Nobody told the AI that rule. It wasn't programmed in. It inferred it, completely on its own, just from those few examples we showed it in the prompt. That's pretty amazing.
So, this is a really powerful proof of concept, but honestly, it's just the beginning. The project already has a super clear roadmap for what's coming next.
And the future possibilities here are just wow. We're talking about more advanced prompt engineering, basically having more sophisticated conversations with the AI. They're even looking into reinforcement learning, so the model can actively learn from its own successes and failures. I mean, imagine an AI that knows the specific error profile of a specific quantum chip and optimizes circuits just for that chip. The end goal, of course, is to scale this whole thing up to tackle much bigger, real-world problems.
So what we've really seen here is an AI learning to improve the very language that quantum computers speak. And that creates this incredible feedback loop, right? Our two most advanced kinds of computing are starting to help each other get better. This is just the start. And it leaves us with this huge, tantalizing question. As AI and quantum computing keep evolving together, what currently unsolvable problems are they going to crack next?